So you're live now.
Wait, no one has come. We'll go live only when few people join. Right now, only three are there.
Yes.
So wait, you can see how many people have joined. Then you make it live.
No, sir. We are starting on time, sir.
No, no need to start on time. Okay, because we are ready to start on time, but no, there are no participants. If there are no participants, no point in starting, right? It's for them, not for us.
You can speak your side, sir.
No point in speaking just like that because there are no questions also.
Okay, sir.
Hmm.
Will we wait, sir?
You will wait for 5-10 minutes. If people come, let's start. Okay.
Yes, sir.
I will tell you. Then you can make it live. You
Sir, you are
tell.
live now, sir. We can stop here, sir.
Hmm?
We can push here for the.
Okay. You can start. What I will do is I will start writing something on chart.
Yes, sir.
Okay.
Session is already live, sir. You are live now, sir.
Okay. So those who have joined, please write your name on chartboard and also from which college you have come and what you are studying. And also, if you have any question, please write it down so that I shall answer them. Unless you start asking questions, okay, I cannot start. Hi, Saurav, you are from which place? Maumita, you are from which college and what you are studying uh, for your upcoming exam? Very good. Which exam that is? Saurav, what you are studying? Oh, exam of this course. Okay, that is fine. But you know, what you are studying in college? Okay, you are in BSc, BSc first year, second year, final year, or MSc. How about Mamita? What you are studying? other than preparing for this course examination that's due in March, sorry, April. I think it's on April 18th, I believe. Okay, so keep writing the questions that you have in your mind as far as this course is concerned. Before that, I shall start discussing one such question that sometime back one of you asked, okay, about steric number. And do we have to consider double bond and triple bond while deciding the steric number? That was the question. Okay, that's an interesting question. And you should remember, steric number originates from the bonding concepts valence-shell electron pair repulsion theory, that is VSEPR. So VSEPR came into picture after finding Lewis dot structure is incomplete in explaining anything and everything about a molecule other than counting electrons and putting four pairs of electrons surrounding it. Okay, it doesn't say anything. Okay, that's Lewis dot structure. And it doesn't explain really many things like shapes and geometry and reactivity and properties. So, uh, another concept was brought into picture, that is valence shell electron pair theory. So that deals with steric number. Steric number is nothing but the number of lone pairs and bond pairs at the central atom. Depending upon how many such steric number is there, you can designate a particular geometry. For example, steric number 2, linear geometry; steric number 3, irrespective of lone pairs or bonded pairs, trigonal planar; 4 can be square, tetrahedral; 5 can be trigonal, bipyramidal; 6 is octahedral; and 7 is pentagonal, uh, pyramidal, or pentagonal. Yeah, 7 is okay, pentagonal pyramidal, and uh, pentagonal bipyramidal, and 8 is square antiprismatic, something like that. So here steric number, you should remember, considers only bonded pair and lone pair. And when we talk about bonded pair, it is considering only the sigma bond. Okay, so sigma bond only should be considered. The primary bond the central atom makes with the peripheral atoms plus lone pairs. Okay, so example, if you take carbon dioxide, okay, carbon is surrounded by two oxygen, so it's and it carbon doesn't have any lone pair, the steric number is 2, so we are not considering the double bonds. Okay, you should ignore double bond. Same thing is true in case of acetylene, and also same thing is true in case of HCN also. For example, if you consider SO2, since we have a lone pair and we have two bonded pair and one lone pair, ignoring double bond, its steric number is 3. So this is how it goes, and you should not consider pi bonds for counting steric number. Okay, that you should remember. Is that clear for you? So if you have any other question, please write on the chart board so that I can answer. And someone asked about uh, how do we take preparation for our exam? Yes. And see, exam has several components. Main group chemistry is one such component, unless the paper is about main group chemistry. Okay, if it is a general chemistry, it has main group chemistry, transcendental chemistry together, and also some other aspects. So when you are preparing, just listening to me is not good enough. And of course, I must have shown a lot of worked examples, and also assignments are also given. Apart from that one, you should also read the recommended textbooks such as Shriver and Atkinson, okay, and also CES Housecraft and Sharpie. So these books really help you to prepare, okay, to write either this exam or any competitive exams you are looking for. So any questions you people have now? Momita, Saurav? So this live session is meant for you people to clear any doubts you have in your mind. If you people keep quiet, I cannot take it further. Okay. So if you do not have questions also, then write it down. I do not have any doubt. Then I appreciate. And if you have questions, please bother me. Yeah, any suggestion for your upcoming exam? That's what I told you. Okay, don't worry about what kind of questions comes, and if you are sound with your basic knowledge, no matter how questions are given, you should be able to answer. Whether it's a GATE exam, whether it's a CSR exam, or whether your BSc, MSc exams, or this exam. Okay, and if you have answered thoroughly all assignments, that should help you in getting better grade. And if you are writing competitive exams along with this main group chemistry course, there is one more course running, that is interpretive molecular spectroscopy. That's equally important, and hundreds of questions are there in it based on spectroscopic methods and analytical methods. And if you go through them and answer those things and solve those, I'm sure you should be able to pass CSIR, JAM, or any other exam, GATE exam, without any difficulty. Okay, so that has hundreds of questions on, molecular spectroscopy. Please look into it. They are on YouTube. If you have not registered for that course, you can just look into it. You consider a simple molecule such as HF, okay? And if I ask you to write the geometry of F, how do you write it? Okay, you cannot say it's linear, okay? So if you let's look into HF, a pair of electrons are involved to establish a hydrogen to fluorine bond, and fluorine has three pairs of electrons. So if you just look into it, it has three lone pairs and one bonded pair. So geometry should be tetrahedral. Okay, and shape is linear. So three lone pairs are disposed to three corners of a tetrahedron, and one is a HF bond. So this is how you should look into the molecules according to the bonding concepts. And if you go through valence bond theory, again, if I have to tell what hybridization F has undergone in making HF molecule, we should say sp3 hybridization. Out of sp3, one sp3 is involved in HF bonding. Other three sp3s are accommodating three lone pairs of fluorine. Okay. One has one electron. Out of four sp3, three sp3 have two electron each, and one has one electron, and that interacts with one s1 of H. so that still you can use valence bond theory to explain bonding in HF. Kevin, what you have any question? You came late, it seems. It's Kevin 884. So who has joined later? Please write down your name. So I will give you another 5 minutes, okay, to ask question. If you don't ask, I have to close the session. So you should utilize this opportunity to get your doubts clear. Otherwise, I think you have understood very well my course. I will be very happy to know about that one. Or you are not reading it properly. So Kavin, you have any questions? Or anything else needs to be added to this course? That also you can tell. When I revise it, I will keep those things in mind. Okay, that's a good question. If electronegativity decreases down a groove, then why do aluminum and silicon? Okay, if you see aluminum and silicon have lesser than gallium and germanium. Okay, so yeah, I have to check the values may be very marginal. The difference is very marginal. I will tell you. Uh, I will write down the values. Then I should be able to explain. Yeah, so okay, so I will give you the values. Well, aluminum shows electronegativity from different scales, okay, 1.5 to 1.6, okay, and then silicon is about 1.9, okay. So yes, when you are going from aluminum to silicon, yes, electronegativity increases because of increase in the number of electrons, okay, and also the nuclear charge, okay. So then gallium comes below aluminum, that's 1.6. So basically, if you consider aluminum 1.6 and then gallium 1.6, there is not remarkable difference is there. That difference is very marginal. Aluminum is between 1.5 to 1.6, and gallium is 1.6 to 1.8. Okay, so the marginal difference is there. Okay, I um, and if you go for germanium, it's 2.01. Okay, it is a little bit more compared to silicon. It should have been little less. Okay, but why that happens is when you go for gallium, the 3D orbitals are coming into picture. Okay, when the 3D orbitals are coming into picture, what happens? Uh, the deep black 3D whatever is there, that contraction results in what happens? Valence electrons coming very closer. In that case, what happens? It can readily take an electron because of increased effective nuclear charge. Okay, it can take an electron easily. That means that's the reason electron activity increases in case of germanium, and this property we are using in semiconductors. That's the reason this germanium and gallium are very important semiconductors. These little bit of anomaly you see has to do something with the three orbitals, 3D introduction of 3D orbitals, and they contract very well. And in that case, what happens? Valence electrons are pulled a little bit closer, and hence effective nuclear charge increases, and hence electronegativity also increases to take one more electron. Okay, the elec- so electron negativity means electron accepting or enthalpy they say. So that is little bit more pronounced in these cases. Okay, so that's the reason. It's not exactly an anomaly. Yes, you can say if you go with periodic trends and periodic properties, it's an anomaly. But many times we see these things happening. For example, if you look into nickel, palladium, and platinum, okay, nickel has 3D8, 4s2, and palladium, what happens? 3D10, 4D10, 5s0, okay. And then if you go to platinum, 5D9, 6s1, it becomes. Okay, so this is some sort of anomaly. Then on the other hand, you should also see the diffusion and of orbitals increase in the orbital size, and also the F electrons coming into the picture, lanthanide contraction. As a result, what happens when the size of orbitals are more or less similar, then the electrons can move very easily, and in that case probably what happens, to enhance metallic bond, it generates an electronic configuration where you can have metal metal bond, stronger metal metal bonding interaction. So this looks like anomaly, but there's an experimental evidence is also there. Since experimental evidence is there, we should be able to explain. Okay, it does not happen with phosphorus arsenic. Yes, yes, strictly speaking, it should not happen with gallium and germanium and aluminum and silicon also. That's the reason it's bit, you can also say it's an anomaly what we see in case of ionic radius, okay, and electron enthalpy, ionization enthalpy decreasing among the 3D in between and then increasing again. That has to do something with half-filled electronic configuration and complete electronic configuration. So in the same way here also, certainly this is an anomaly, but you can explain the way I said. But certainly phosphorus and arsenic follow strictly periodic trends. So as sulfur and selenium, you don't see that one. Why should oxygen coming as second position for electronegative? Okay. Yes. Yeah. So if you see, according to arrangement of orbitals and all those things, you can see once after nitrogen, okay, this p and s orbital will interchange. That you must have seen. I have already given in one of my uh, earlier talk. Okay, and then oxygen is actually, so you should remember that one. Next to oxygen, fluorine is coming. Okay. And here what we have is 4s2, 4p4, and then we have 4s2, 4p5. Obviously, electronegativity is increasing in the first row elements, and nitrogen is more electronegative compared to nitrogen. Oxygen is more electronic because the electrons are added to the same subshell. Okay. And then fluorine comes ultimate, that is. Okay. The electronegativity is next to, obviously, since oxygen is neighbor of fluorine, okay, and obviously it poses high electronegativity because of higher effective nuclear charge. And then chlorine comes. Chlorine is more or less comparable to that of nitrogen. Okay, so it is not anomaly or anything. It's according to the periodic trends. Okay, oxygen being very close to, okay, fluorine is the second, okay, uh, highest electronegative element in the periodic table. The interesting thing is, if any other element in the periodic table other than oxygen and fluorine, they cannot, if they are existing in higher oxygen state, highest possible oxygen state, okay, they should be bound to oxygen or fluorine. And of course, when oxygen binds to fluorine, oxygen shows positive oxygen states, O plus and O2 plus. Okay, oxygen can show positive oxygen states only when it is bound to fluorine. For example, similar to H2O, if you have uh, O, OF2, okay, yeah, O2F, their oxygen will be in positive oxygen states. Okay, if only oxygen shows positive oxygen state when it is bound to fluorine. Okay, so, and it is 4.5 and it comes around 4, and nitrogen comes around 3.5, and so as 3.4 to 3.5 in case of chlorine. So it follows that trend is expected. There is no anomaly in it. Is that all? Is it clear for you? So any other question? So, you see, MO diagram I've already given for SF6. Okay. And then, of course, it is a very interesting question. And I have given emphasis to understand the bonding in case of SF6. And SF6, the moment you see S bound to 6 fluorine atoms, okay, uh, valence bond theory says it is sp3d2. Okay. And it says octahedral. Okay. And also it is less reactive compared to SF4. SF4 has a seesaw structure, an excellent example. Well, you can refer to the diagram already have shown. Okay. So in this case, what happens? Why And if you just look into the MO diagram I have given, that would say clearly uh, in this one, the S and P orbital, okay, are much farther from 3D orbital. Okay, 3D orbital is quite far. Okay, and the energy of d orbitals is much higher compared to S and P. As a result, there is no scope for SF6 S to undergo sp3 due to hybridization. Okay, but somehow valence bond theory, in the moment it sees coordination number 6, it says it is sp3d2. It's totally wrong. Okay, in this one, what happens? Still, S and P orbitals are combined together to accommodate, okay, having 4 electrons, expecting 4 electrons from fluorine, okay, to have, okay, 4 covalent bonds. Then what would happen? 2 more fluorine atoms, they essentially take the electrons from S and they stay a little away from in the axial position. Okay, so let me write the, okay, let me share you that diagram here. Can you see now the blank slide? Say yes if you're seeing. Yeah, so yes. So here, basically, 3s, 3p, and 3d. Is that right? In case of S? Yeah, so if you see this energy difference, sorry, okay. So here, if you see energy difference is very high, and if at all, if there is a, according to valence bond theory, first I will go to valence bond theory. So it should be sp3d2, but there is no scope for 3p and 3s to so form with 3d. So this is very high in energy. So as a result, what happens? This you can see here. Uh, yeah, I should write in a proper way. It should something like this. It should appear. Okay, so that means basically it can still establish, 4 SF bonds, and then other will remain essential as F minus F minus. Okay, a little farther away from, but this can happen in any direction. Okay, in X, that's the reason what happens. It looks uh, symmetric in all directions. Okay, uh, very similar to what you come across in case of XEF6. SCXF6, if you look into XEF6, okay, it has, okay, one pair of electron is there. So if you take 8 plus 6, 14 are there. 14 means 2, 7 pairs are there, skeletal electron pair. So here, one lone pair, one bonded, 6 bonded pairs are there. It is not octahedral, it's capped octahedral. This electron goes to one of the uh, triangle positions. But this one, what happens? This can move around about all the 8 triangular positions. As a result, what happens? It looks very symmetric. Same thing happens in case of, so this can happen to this one, or this can happen to this one, or this can happen to this one. As a result, it appears very symmetric. And then since it is surrounded by 6 fluorine atoms, reactivity is less. That's the reason it's not vulnerable for hydrolysis the way SF4 undergoes. But on the other hand, heating, the moment 2 detaches, okay, it will be as reactive as SF4. Okay, so since the difference is very high, it's highly unlikely that d orbitals will come into picture. So this is a hypervalent molecule. Okay, this is a hypervalent molecule. Very similar to Na2SiF6. Okay, this is another example. Na2SiF6 also hypervalent molecule, but we say silicon is octahedral and it's surrounded by 6 fluorine atoms, but it's a hypervalent molecule. Here also, in case of silicon also, these two F will be negative, and that negative charge is balanced by 2Na. So these are all, SF6 is a hypervalent molecule. Whatever the geometry predicted from valence bond theory as octahedral is wrong. But however, because these things, whatever I have shown here, can happen in all 6 directions. As a result, it is symmetric, and hence it looks like a symmetric octahedral molecule. Otherwise, strictly speaking, it's an hypervalent molecule, and d orbitals are not at all participating in the bonding. And please look into the MO diagram already I have given in it. Okay, if you still have doubt, you can look into CS Housecraft inorganic chemistry. They have given this diagram once again. Okay, is that clear? Any questions? So any other question? Kavin or Momita?
Yes, sir.
Yeah. No, I'm asking if there are any questions from their side. So if not, shall I close the session so that we can start another one after 15 minutes? So thank you once again. So I will be taking another live session sometime in March. See, see, I didn't discuss about perovskites, fluorides in this one. Uh, See, basically, they follow the spinels and inverse spinel structures. Okay, and maybe in my next when I do revision for this main group, it's beyond the scope of this course anyway. But doesn't matter. Okay, when I talk about some structures and bonding concept, I shall try to introduce this one either in this main group chemistry or in transmetal chemistry. Okay, maybe in the live session that I'm going to take in March, I would try to shed some light on it. If you understand uh, spinel structures, okay, probably you can understand perovskites much more easily and also fluorides. Okay. Mm, so let me close this session. Okay. And see you in March in the second live session of this course. Okay. So thank you.